I'm not going to go into the derivation of this next bit. It is rather standard math formula. Just because I've attempted to explain it in the past, and I think it really hasn't gone over well, so just sort of go with, I'm going to let you sort of trust that this is the case. When I bring wavelength and period both into it, in other words, I have a time and a distance component to it, we'll just do the classic y is equal to some amplitude times the sine or cosine. And just to keep standard with my notes, I think I did cosine, but I don't want to. There's enough places for me to mess up here. Oh, no, I did sine in my notes, so we'll stick with sine. Kx minus omega t. This is the standard formula for a wave, which is not only changing with time, but it's changing with position. It's basically, it's a traveling wave. If it's a standing wave, then I don't have to worry about any shift there. I can tell you at what time the y value is x, or for choice of words, the y value is something. Or if I have a standard wave that maintains its shape and just sort of travels like that, well, I guess that is a traveling wave, but I have to use this. The period is 2 pi divided by the coefficient of the time variable, and the wavelength is 2 pi divided by the coefficient of the x. This omega is the angular frequency. And k is called the wave number.
You said this is a derivation?
We'll get to it. I'm not deriving this. This is sort of a base formula that we need in order to derive the speed of light.
Okay.
Now, this was a non-derivation. I'm just sort of presenting it. Ta-da!
What is K again?
Say it again?
What is
Wave
K?
number?
K is the wave number.
What's that mean?
What does that mean?
Yeah.
In a sense, it's the number of waves that have been created.
Like per period?
Yeah. I think that's safe to say.
So like, well, you're dividing over 2 pi, so wavelength per wave number?
Wait, so if I had, so let's ignore the time component for just a second here. So I have y is equal to 3 sine of 4x. Then the wavelength is 2 pi divided by 4, or pi over 2. That,
Okay.
which means that I'm basically cramming 4 waves in what the space I used to cram 1 into. So the wavelength is a quarter of what it was.
There's more oscillations?
Yes.
Okay.
And then period, similar type reasoning, that if this number is bigger than 1, then I'm cramming more waves into what was originally 1 period. Now, as far as understanding what I'm about to be doing, what I'm going to be doing, first, just accept that this is the formula for a wave, for a traveling wave. And you should know how to do derivatives of sine and cosine. Let's just do that real quick. d sine theta dt. Let's make it sine omega t. d sine omega t dt.
T cosine of WT. Or, no, wait, that would go to 1. So W sine WT.
Omega. Derivative of sine is not sine.
Omega cosine WT.
So omega cosine omega t. d cosine omega t dt.
Is that a negative sign? Well, yeah, negative omega sine omega t.
All right. We're cooking. If I wanted to look at a speed of a wave, first off, what is speed? What's the formula for speed?
dx dt.
All right, the xt works just fine here. All right, delta x over delta t. Distance over time. So if I'm looking at creating a wave here, the distance that that wave travels and the time it takes me to create it is the wavelength. And the time it takes me to create one wave is the period. Flashback to probably sometime around Thanksgiving last semester. So the speed of wave is just the wavelength divided by the period. And the wavelength is 2 pi divided by the wave number, and the period is 2 pi divided by the angular frequency. And so the speed of the wave is also just the angular frequency divided by the wave number. And for those who can't tell, this is a lowercase k, not an uppercase k. And it doesn't make much difference here because I'm using only, I believe only one k in this derivation, unless I'm blanking on something. But k's are used so often that for the purist, it's a lowercase k. So I'm going to put that over here because that's important enough. The speed of the wave is the angular frequency divided by the wave number. We definitely will be using that again. We will not be using these. We will be using these.
What's the angular frequency?
Radians per second. If you think of it as, if I have a wheel that's spinning around like this, then if you look at the x projection of that peg, that's the cosine value, and the y projection is the sine value. Angular frequency, it's basically angular frequency, it's the angular speed at which this wheel is rotating.
Is there a formula for it?
There are loads of formulas. So omega is equal to 2 pi times the linear frequency or regular frequency. That's what, so omega is equal to 2 pi divided by the period, because frequency and period are reciprocals. And then therefore the period is 2 pi over omega, which is written over there. Now there's sort of a chicken and egg argument there, but hopefully it's sufficient. So basically, I'm creating this wave. I have some charge that's oscillating back and forth, creating a wave. The frequency with which it's going back and forth is f, and from which you can find the angular frequency. And then the distance it actually travels in the creation of one of those waves depends very heavily on the speed of light. Or officially at this point, the speed of an electromagnetic wave. Any other questions at this point on what's on the board before I erase? Now you get to see a three-dimensional drawing on a two-dimensional board by me. So as I create this moving electric field, so I have an electric field that's oscillating back and forth and is propagating outwards. This is what is called the amplitude E sub naught. The magnetic field that is created from that is perpendicular to it. That's my attempt at perpendicular to it. Oh. That's not far enough. There we go. So the ones where I've drawn the arrows at a slant, that's to indicate that's basically perpendicular to the board. That is the magnetic field with a magnitude, amplitude of V sub 0. My electric field is up and down. So two very, very different colors here, just to emphasize the difference here. So an electric field going up and down, and magnetic field going left and right. Now, in reality, if I shine the flashlight on you, we don't have electric fields going this way and magnetic fields going that way. We have some, but there are electric fields in all sorts of directions, and the magnetic field that is propagated by it is perpendicular to it. And the wave's traveling that way at some speed c. All right, let's get rid of this stuff.
Is that always the case? Where the electric field moves perpendicular to the magnetic field?
In an electromagnetic wave, yes. So which one do we do first? Let's do this one right here. We'll use Faraday Lenses Law. So Faraday Lenses Law says if I do a line integral of an electric field around a loop, then I should get the negative change in the magnetic flux with respect to time. And so let's do that. So what I'm going to do is I'm going to take a small little section right here. I'm basically going to create, it's a rectangle. I'm going to sort of take a snapshot of the electric field at this point. Now I could do it at any point, but this works just as well as any. In other words, let me draw it bigger. My electric field is traveling. My electric field is up, going up at this point. So my electric field is some size E here, and over here, this is whatever that length is plus some change. There's a difference between these two electric fields. There's electric fields in between, but I don't really care about those, and we'll get to why in just a second. This change right here, make sure I get the right thing, okay. Is dx, and the height here, we'll just say it's on h. So this is it's a virtual rectangle, because when I'm doing my line integral here, it's around some Gaussian loop or Amperian loop. And so I just created a path to do my line integral. At this point right here, my magnetic field is coming out at you. So my magnetic field is coming out at the board, out of the board toward you. Because at that point, my electric field is up, my magnetic field is out. If I'm doing a line integral, I need to start someplace and work my way around. Typically, the way you do it is sort of a right-hand roll. Magnetic field's coming out, so I'm going to do my line integral counterclockwise. So I'm going to start here. I'm just going to call this 1, 2, 3, and 4. So let's start from the basics there. I have my electric field, not dl, is negative d phi b dt. A line integral means I'm doing an integral along each of these paths here. So this is the integral along path 1 of E dot dl, plus the integral along path 2, E dot dl, plus the integral along path 3, E dot dl, plus the electric field along path 4, integral along path 4, E dot dl, is equal to the negative dVA dt. Now, I did play a little fast and loose with a little math bit right over here, so I'm going to justify it. Well, sort of up here. 5b is the integral of b dot dA. My magnetic field is not changing appreciably in this small little region. I mean, again, the width is just dx. Magnetic field is not significantly different. And so it's just dA. A little less fast and loose, just slightly. So I got a dot product here between E and dl. Questions before we start doing the next line? All right, so along this path 1, that's this down here, moving in this direction, moving to the right. What is E dot dl along path number 1? Say it again.
dl becomes dx,
That is true?
and e becomes e plus e changing x, changing e.
If you're going to go that route, well, E is changing as we go. But there's a simpler way of approaching that. What's the direction of the electric field? What's the direction of dl?
The perpendicular.
Therefore,
Zero.
yep, they're perpendicular, so we don't have to worry about what E is along that path.
So it'd be a 0 for 3 as well.
Absolutely. All right, now on path number 2, my electric field is,
E plus delta E.
yep, times H. They're in the same direction. So this becomes E plus delta E. I know I have a delta there. That's because I was doing the 151 version of it. Times H. And then along path 4.
E times H.
Close. Negative. Because my electric field is
Right.
up, but my path is down.
And you're going counterclockwise, so starting from the top. Huh?
Yeah. Minus EH is equal to, now over here, my area is not changing with time, because I said that's gonna be my rectangle right there, and I said it. So this becomes negative area times dV dt. And so if I distribute here, I get HE plus HDE minus EH is equal to negative A times, what is the derivative of B with respect to time? And I did leave off those equations there, so let me write those up. Right, I went through this exercise for a reason, let's connect it up. My electric field is E sub naught sine of kx minus omega t, and B, which is also a traveling wave, B sub naught sine kx minus omega t. They have the same wave number and the same angular frequency because they're traveling together. So what is the derivative of B with respect to time?
Negative b naught omega cosine k lambda minus omega t. So the whole equation becomes positive.
K, that's kx.
Oh, kx, I thought that was lambda.
Just put my lambdas in K, then x is look alike. All right. And so we now take this, we can, well, obviously, HE and EH cancel out. Commutative property holds. So what I'm left with is
Wouldn't it be positive for them?
We lost something here. The derivative would be negative because we got the, we're taking the second
Oh,
time.
right,
because we got
right,
negative
yeah,
there.
okay.
Oh, okay, yeah, one more step to go before we get there. All right, so this becomes HDE is equal to my area, or the negatives cancel out, so my area, and what is my area?
Yeah, it's not H.
Times V naught omega cosine kx minus omega t. My h will cancel out, which is fortunate because I just made up that length h right there, so it's really nice when it goes away and I don't have to worry about it anymore. H goes away. I'm going to divide both sides by dx. And so I have the e dx is equal to v naught omega cosine kx minus omega t. And what is d e dx?
E sub naught K cosine kx minus omega t.
So just applying Faraday Lenses Law to our situation here of an electromagnetic wave, it does simplify down quite nicely. The cosine kx minus omega t goes away. So I have E naught K is equal to B naught omega. And I'm going to bring K over to the right and B naught over to the left, and so I get E sub 0 over B sub 0 is equal to omega over K, which is the speed of the wave. Obviously, we're not done yet because it doesn't look anything like the formula I gave you the other day, but we do have that the speed of the wave is just the ratio of the amplitude of my electric field divided by the amplitude of my magnetic field. That is something that we'll come back to, so I'll write that over here. I think it's off camera, but I'm just pointing to what I'm writing down. Questions to hear? And again, this is the halfway point in the derivation. All right, so I'm going to erase this. So now what I want to do is I want to take a look at the magnetic field, and I'm going to do it from sort of the exact same spot. I'm going to take my rectangle looking like that. So I have my electric field, magnetic field coming at you, and now I'm just going to look at it this way. So my magnetic field is now going to be pointing upwards. Oh, it's still going to be dx. This is h. My magnetic field. Over here, it's some magnitude of B, and over here, it's B plus dV. My electric field is pointing into the board, because again, from this drawing right here, I've got an electric field's got the ring on it, magnetic field does not. And so when I tilt it this way, my electric field is pointing towards the board now. Or into the board. We're going to employ the Ampere's law with the Maxwell correction. Well, it has to be with the Maxwell correction because we don't have actual charges flowing here in our scenario. So this part is zero in our case right here. I'm more concerned with the change in the electric flux. So we're going to go through a very similar process to what we have right there, but it's enough different that I probably should erase. And so my line integral of B dot dl is equal to u sub naught epsilon sub naught d phi e dt. Now if I'm doing a line integral, I need to have some particular path, starting point and ending back at the same point because it's a closed loop. I'm again going to start here in my lower left-hand corner, and again using sort of a right-hand rule, I'm going to go clockwise. So I'm going to do my loop around like that. So path 1 is here, 2, 3, and 4. As I go clockwise around this loop, so I have the integral of 1, b dot dl, integral 2, b dot dl, plus the integral 3, b dot dl, plus the integral 4, b dot dl. It's basically my line integral along each segment of the path. And that's going to be equal to mu naught epsilon sub naught dE dt. Same rationale I had before, just making it BE in the last case. Questions to hear? Start taking our paths. Path number 1, what is the integral of b dot dl along path 1?
BH.
Yeah. It's just magnetic field times H. Along path 2?
0.
Along path 3?
B plus B.
Negative H times B plus dV. And then path 4? And that's going to be equal to over here. My area is not changing with time, so that just comes out. So I get u naught epsilon sub naught A dE dt. And so we get BH minus BH minus HdV equals mu naught epsilon sub naught times my area, which is the physical area of my virtual rectangle here, which is h dx, times, well, what is the derivative of the electric field with respect to time?
Is e sub naught omega cosine kx minus something t.
What's the beta 252? You're missing something. Yeah, negative. Because the minus sign right there.
Right.
So we get negative h dv is equal to mu naught epsilon sub naught, oh, h is going away. Dx, the minus signs go away. E naught omega cosine kx minus omega t. Divide by dx, just like before. So we have dv dx equals mu naught epsilon sub naught e sub naught omega cosine of yada yada yada. What is the derivative of b with respect to position?
K, P dot, cosine, KX minus omega t.
And like before, the cosines go away. Officially, we're not dividing by the cosines. We have two cosine functions on each side, and if it's always equal, the coefficients must be equal. So what we're technically doing is just looking at the coefficients of cosine, but I just like slashing through it. So I'm left with k b sub 0 equals mu sub naught epsilon sub 0 e sub 0 omega. Again, like before, I want to find the speed of this wave, and so I'm going to get omega over k, so I'm bringing k over this side, I'm bringing this over to the other side, and so I get omega over k is equal to b sub naught, u sub naught, epsilon sub naught, e sub naught. And that, based upon what we did the last time, is equal to e sub naught over b sub naught. At this point, it's just a tiny little math problem here. I know e sub naught over b sub naught is the speed, which I'm just labeling as c. And over on the other side, it'd be 1 over mu sub naught epsilon sub naught c, because I've got basically the reciprocal of c right there. Multiply both sides by c, I get 1 over mu sub naught epsilon sub naught is equal to c squared, or c is the square root of 1 over mu sub naught epsilon sub naught. And that's the equation I wrote on the board last week.